For decades, robots have existed as obedient machines, precise, tireless, but fundamentally mindless. They could weld, assemble, and repeat the same motion endlessly, yet they never understood what they were doing. And then, inside a quiet but revolutionary facility at Tesla, a different question began to take shape. What if a robot didn't just execute commands? What if it could think? Optimus was never meant to be just another industrial robot. From the very beginning, Tesla's ambition went far beyond motors, metal frames, or balance algorithms. Their true focus was invisible, the creation of a digital brain capable of perceiving, learning, and reasoning about the world in a human-like way. Because without intelligence, a humanoid robot is nothing more than a mannequin that moves. Traditional robots rely on rigid programming. Every movement is predefined, every action anticipated. But the real world doesn't work like that. Humans drop objects, change their minds, create chaos without warning. A robot designed to operate alongside us cannot depend on scripted instructions alone. So, Tesla made a radical decision. Optimus would not be programmed, it would be trained. The foundation of this robotic mind comes from the same artificial intelligence that powers Tesla's self-driving technology. But there is a crucial difference. A self-driving car needs to understand roads, signs, and traffic behavior. Optimus must understand the human world itself: tools, spaces, body language, intent, and uncertainty. This is where the challenge truly begins. Teaching a robot to walk is difficult. Teaching it to decide when to walk is exponentially harder. Every step requires judgment, balance, force, intention, and awareness of surroundings. For humans, this happens subconsciously. For a machine, it must be learned from scratch. Tesla calls the place where this learning happens the Optimus Brain Factory. It isn't a factory that produces physical objects. Instead, it manufactures intelligence neural networks trained to interpret reality, predict outcomes, and choose actions without explicit instructions. Here, Optimus begins life with no knowledge. No instincts, no common sense, only algorithms capable of learning patterns. And that raises a profound question. If intelligence is no longer hard-coded but learned through experience, what separates a machine's mind from our own? Inside the Brain Factory, Optimus is designed to observe the world the way humans do through vision, spatial awareness, and continuous feedback. It doesn't memorize actions. It learns relationships, how objects behave, how gravity works, how small mistakes lead to big consequences. This is not automation. This is cognition. And yet, intelligence cannot exist in a vacuum. A brain without experience is nothing more than potential. To truly think, Optimus must be exposed to the raw complexity of reality. So where does that experience come from? How does a robot learn what it means to exist in a human world it has never lived in? Can a machine truly understand reality simply by watching us, or does intelligence require something more? The answer lies in data, and an ocean of it. Intelligence does not emerge from code alone. It is shaped by experience. For humans, learning begins the moment we open our eyes. We watch, imitate, fail, adjust, and try again. And at the heart of the Optimus project, Tesla made a bold
Unit
assumption:
71 is performing
a robot should learn
flawlessly
the
after the
same
reset.
way. Instead of feeding
The new
Optimus a
pathfinding
list of
parameters are holding
instructions,
steady.
Tesla feeds it something far
Proximity
more
sensors
powerful
holding
data
steady
from
at
the
50
real world.
centimeters.
Every day,
Behavior
humans
profile
perform
looks good.
thousands of
No
actions
sudden
without
movements
thinking.
detected.
Reaching for a tool, lifting a box, avoiding an obstacle, adjusting grip when something slips. These movements may look simple, but each one contains an extraordinary amount of hidden intelligence. Balance, force, timing, intent, all happening simultaneously. For a robot, none of this is obvious. To teach Optimus, Tesla collects massive amounts of real-world data using cameras, sensors, and motion capture systems. Human actions are recorded not just as movements, but as spatial relationships, how objects exist in 3 dimensions, how they change over time, and how humans adapt when reality doesn't behave as expected. This data does not tell Optimus what to do. It shows Optimus how the world works.
The torque setting
the
is
robot
correct.
learns that a cup can spill,
Okay,
that a
Robot
surface
1,
can be
assist
slippery,
with placement.
that an object may be heavier than it looks. It begins to associate vision with consequence. A critical step toward genuine understanding, but data alone can be dangerous. Too little data, and the robot becomes naive. Too much poorly labeled data, and it becomes confused. One of the greatest challenges in building Optimus is teaching it context. When a human bends down, is it to pick something up or to avoid hitting their head? When an object falls, should the robot catch it or step back? These decisions require judgment, not rules. That's why Tesla focuses heavily on perception. Optimus doesn't just see pixels. It interprets depth, motion, and intent. It learns to predict what will happen next, not just react to what already happened. This predictive ability is the first sign of something remarkable. When Optimus sees a human reach for an object, it begins to anticipate the outcome. When it observes instability, it prepares to adjust. In essence, the robot starts to imagine the future, a core trait of intelligence. Yet there is a problem. The real world is messy, unpredictable, and often unsafe. A robot cannot be allowed to learn from dangerous trial and error among humans. One wrong move could cause serious harm. So Tesla faces a critical dilemma. How do you give a robot real-world experience without exposing the real world to risk? The answer lies beyond observation, because watching humans is only the first step. To truly learn, Optimus must act and fail at a scale no physical environment could ever allow. If a robot cannot safely learn in our world, where can it learn without limits? The next chapter takes us inside a universe where failure is not only allowed, it is essential. Deep inside Tesla's AI infrastructure, intelligence is not written, it is grown. This is where the Optimus Brain Factory truly comes to life, powered by vast computational systems designed for one purpose: training a mind. At the center of this operation is Tesla's neural network training ecosystem, built to process unimaginable volumes of data. Millions of real-world observations flow into the system every day, where they are transformed into learning experiences for Optimus. This is not traditional programming. There are no explicit instructions like pick up the object or avoid the obstacle. Instead, the robot's brain learns through continuous feedback. Every action Optimus attempts is evaluated. Did it succeed? Did it fail? Was the movement efficient, stable, or dangerous? The neural network adjusts itself, strengthening some connections, weakening others, slowly shaping behavior that looks less like code and more like instinct.
Clear the bay door.
This
Next truck
process
is pulling
mirrors
up.
how biological brains develop.
Roger that.
Humans are not born
Scanning this
knowing how
pallet
to
now.
walk or
All
grasp
accounted
objects. We stumble, fall, and adapt. Optimus does the same, but at a speed no organism could ever match. Tesla's approach allows Optimus to experience millions of failures without consequence. Each mistake becomes a data point. Each correction brings the system closer to competence. Over time, patterns emerge. The robot learns balance. It learns coordination. It learns timing. And then, something remarkable happens. Knowledge becomes transferable. When one version of Optimus learns a better way
Great
to
to finally
perform
see
a
these
task,
Optimus units
that
arriving.
learning does not stay
We're ready to
isolated.
start the deployment process.
It can be instantly shared across future robots. Unlike humans, whose experiences are locked inside individual minds, Optimus learns collectively. Progress compounds. But
Okay,
intelligence
team, listen
is
up.
not
We've
just
got the
about
Q3
success.
targets posted here.
It is about
The
dealing with
Optimus units are
uncertainty.
fully charged
Tesla
and ready for
deliberately
deployment in
exposes
aisle 4.
Optimus to ambiguous scenarios, unclear object shapes, partial visual information, unexpected resistance. These situations force the neural network to make decisions without perfect data. In other words, Optimus learns to reason under uncertainty. This is a critical threshold. A robot that only works under ideal conditions is fragile. A robot that can adapt when conditions change begins to resemble intelligence. Yet even with immense computing power, there is a limit to what can be learned from real-world data alone. Physical testing is slow, expensive, and risky. Training a robot purely in reality would take decades. So Tesla pushes the brain
Keep 'em coming,
factory
we're stacking
beyond the
row
physical
3 now.
world. They create
Make sure those
environments
Optimus
where
boxes
time
are
can be
secure.
accelerated, physics can be manipulated, and failure carries no cost. Virtual worlds where Optimus can attempt the impossible again and again. Because true intelligence is
All right,
forged
where do you
not
want
in
this one?
perfection, but in controlled
Set it
chaos.
right here by the yellow
If
line. I'll
Optimus
scan
can
it
learn
now.
faster than reality allows, what happens when its virtual intelligence meets the real world? The answer lies inside a universe built entirely from simulation, Before Optimus ever takes a step in the real world, it lives thousands of lifetimes in a world that doesn't physically exist. Inside advanced simulation environments
7B
developed
is
by
fully
Tesla,
synced.
reality is rebuilt
Pushing
from
the
code.
localized update now.
Floors, walls,
Check the manifest for
tools,
deployment
gravity,
priority.
friction. Every detail is recreated with obsessive precision. This is not a video game. It is a training ground for intelligence, where mistakes are not punished, but encouraged. Because in the real world, failure is expensive. In simulation, failure is priceless. Here, Optimus can fall without breaking. It can misjudge weight without injury. It can collide,
Look how smoothly it
slip,
moves.
lose balance, and
Yeah,
recover
they're much
millions
quieter
of
than I
times a day.
expected.
Time itself is accelerated. What would take years of physical testing can happen in weeks. This is where the robot learns resilience. Tesla's simulations expose Optimus to
Yeah, they have
endless
the best deals on
variations of
these.
reality.
Where is the garden center
Objects
these
change
days?
shape.
It's
lighting
actually
conditions
right around the
shift.
corner.
Surfaces become unstable. Unexpected forces appear. The robot is forced to adapt, not memorize. Every scenario pushes the neural network to generalize rather than overfit. In other words, Optimus doesn't learn one world. It learns how to survive in any world. One of the most critical lessons taught in simulation is recovery. Falling is inevitable even for humans. The difference between intelligence and fragility is the ability to get back up. Optimus practices this relentlessly. It learns how to shift weight, brace impact, and reorient itself after failure. This ability to recover marks a turning point. A robot that avoids failure becomes cautious and limited. A robot that understands failure becomes capable. Simulation also allows Tesla to test extreme scenarios no human
Look
environment
how
could safely
smoothly it
provide.
moves.
Sudden obstacles, unstable loads, conflicting
It really
objectives.
does fit
These
perfectly
edge
with the
cases
decor.
are rare in reality, but when they happen, they matter most. Optimus learns to prioritize, to choose between competing actions, to abandon a plan when conditions change. This is decision-making, not automation. Yet, there is a hidden danger in simulation.
How
no
was
matter how
everyone's
detailed
day?
a virtual
This smells
world
amazing.
becomes,
It was
is
good,
still an
busy though.
approximation.
Are you
Tiny
hungry, sweetie?
inaccuracies in friction, timing, or visual noise can create a gap between simulation and reality. A robot that performs perfectly in a virtual environment may fail catastrophically in the real one. Tesla calls this the reality gap. Bridging it requires constant calibration between simulated experience and real-world feedback. Data flows both ways. Reality corrects simulation. Simulation prepares the robot for reality. Together, they form a learning loop that tightens with every iteration. And eventually, a moment arrives when Optimus no longer behaves like a machine being tested. It behaves like an entity ready to be released. But the final question remains. After learning in worlds where nothing is truly at stake, what happens when Optimus steps into a world where everything is? Is intelligence forged in simulation strong enough to survive reality itself? The answer is revealed the moment Optimus leaves the virtual world behind. The moment Optimus steps out of simulation, everything changes. For the first
Confirm the
time,
alignment on
there
that
is no
component.
reset button,
Looks good from
no
here.
accelerated
Proceed
time,
with the weld.
no perfectly controlled variables. Gravity is real.
It's nice to actually
Objects
relax
break.
during break,
Humans
now that the
move
robots handle the
unpredictably.
heavy lifting.
This is the point where
Yeah, I appreciate
intelligence is
that.
no longer
Makes a huge
theoretical.
difference.
It must perform. Inside controlled environments built by Tesla, Optimus begins its real-world trials. It walks across factory floors. It handles tools. It navigates spaces designed for humans, not machines. Every action is now governed by consequences. And yet, something remarkable becomes visible. Optimus does not behave like a traditional robot. It pauses. It adjusts. It hesitates, not because it is confused, but because it is evaluating. The robot observes its surroundings, predicts outcomes, and selects actions based on risk and intent. This is the first sign that the brain factory has succeeded. When Optimus lifts an object, it does not rely on a predefined grip. It adapts based on weight, shape, and balance. When something unexpected happens, a drop tool, a shifting surface, the robot responds without freezing. It recovers. These are not scripted actions. They are learned behaviors. What makes this moment profound is not what Optimus can do, but how it does it. The robot operates with a form of situational awareness, a primitive but genuine understanding of cause and effect. It knows that mistakes matter now, and that behaves accordingly. Still, Optimus is not perfect. Every real-world interaction feeds back into the brain factory. Failures are analyzed. Edge cases are recorded. The neural network continues to evolve. Deployment is not the end of learning, it is the beginning of a new phase. Unlike humans, Optimus does not forget. Every experience can be shared, scaled, and improved. Each version becomes smarter than the last. Intelligence compounds. This raises a question far bigger than robotics. If a machine can learn from the world, adapt to uncertainty, and improve collectively, at what point does it stop being a tool and start becoming a collaborator? Tesla envisions Optimus performing tasks that are dangerous, repetitive, or physically exhausting, freeing humans to focus on creativity, strategy, and care. But history reminds us that transformative technologies reshape society in unexpected ways. The arrival of intelligent humanoid robots will not be just a technical milestone. It will be a social one. Optimus does not think like a human. It does not feel